This is problem 7-61. It's on page 353. The compound beam is fixed supported at A, pin connected at B, and supported by a roller at C. Draw the shear and moment diagrams for the beam. Now this is an interesting one. I picked it out because it's a little bit unique. So let me sketch it here. It's a beam that's really made of two segments. So the beam is cantilevered to a wall, has length 3 foot, at least for this section. Point A, point B is out here at the end of 3 feet, but there's a pin connection to the remainder of the beam that continues on a further 6 feet. So my scale's not very good, but there we go. So out here at point C, there's a roller to support the remainder of the beam, and then there is a distributed load along the entire length of the beam, magnitude 500 pounds per foot. So the question becomes, what do the shear and moment diagrams look like? And what else is going on with this beam? Because obviously if we're going to size this beam, we want to make sure it doesn't fail due to the internal stresses. So what I'm going to do is break this up into two free body diagrams. For the first segment, I'll call it segment 1, we'll have a reaction at the wall at A and then a moment at A as well. Notice it's a counterclockwise moment in the orientation I've drawn it. Probably should move it over just a bit. There's a distributed load, obviously, along the upper section of this beam, or this segment, 500 pounds per foot. And then there must also be some force between these two, right? One's pushing up on the other one's pushing down on the other. Which is which? I don't know. It doesn't matter right now. I'm just going to assume that this beam segment is pushing down at B, which should make some sense, right? Because if the first segment is cantilevered, it can actually support that load, whereas obviously if AB was pushing down on the second segment, well, the thing would just turn. There's no support on the left-hand side. So B has to be a point that provides support for the second segment. So the second segment must be pushing down. I don't know how much or how hard, but there we have it. And then segment 2 will be the remaining portion of the beam. Let's not forget we've got our points A, B, B, C. And because of equal and opposite forces, force F must be pushing up on point B for segment 2. There's still the distributed load along the entire top section for this segment. And then there's also some reaction at C. Now, for whatever reason, I called it C rather than the reaction to C, but I guess it'd be better to call it RC. I'll try to keep that consistent. So what I'm going to do is, first of all, sum forces in the Y direction for the sake of trying to figure out what's going on with segment 2. So what do we have? Well, we have F acting up and RC acting upward, and then minus 500 pounds per foot times a total span of 6 feet. So there's our resultant load. This sum should come out to 0. Basically what this says is that F plus RC is equal to, well, 6 500ths or 3,000. So F plus RC is 3,000 foot-pounds. Okay? Now if we sum moments about a particular point, well, what point would we take? Well, I don't know, maybe B or C, it doesn't really matter. If we sum moments about B, then what we'd find is that RC would be half of this distributed load, be 1,500 pounds. And just by looking at this, and if I drew it this way, it might be easier to see. This is a symmetrical beam, so F and RC are going to be equal. That's what we find from summing moments. And so basically what that tells us is that these two are both equal to 1,500 foot-pounds, or excuse me, 1,500 pounds. Okay? what? That wouldn't be right. Yeah, it may be right, but yeah, it is right because I made a mistake here. I wrote foot-pounds. I'm sorry. This should just be pounds. There we go. I don't know why I put moment units. That was wrong. So anyway, there we go. We've got the magnitude of the reaction at C and the magnitude of F. Now that we've got the magnitude of F, we should be able to tackle segment 1 and see what happens there. So let's start off the same way. Some forces in the y direction. What do we have? Well, RA minus F. And then minus 500 pounds per foot times 3 feet. That's it, right? That's all of the forces acting on segment 1. So, since we know the magnitude of F, we can solve for RA. Say RA is equal to F plus, well, 5 times 3 is 15, so 1,500 pounds. So RA is apparently 3,000 pounds. Not the ideal setup for a problem because you see 3,000 here and 3,000 there, and well, just the way that it's set up. But the reaction at A is 3,000 pounds. Then if I sum moments about point A, taking counterclockwise as positive, well, what all do we have? Well, we've got the moment of F minus F times 3 feet. We've got the moment of the resultant, so let's calculate the resultant. Of course, it's going to be a negative moment as well, because that resultant acts there in the center at half of 3 feet. So let's get the resultant. 500 pounds per foot times 3 feet. That's the resultant. And we want the moment arm of that resultant, which is 3 feet over 2, so 1.5 feet. Is that it? I mean, after all, those are all the moments of all the forces. Well, actually, there's one more thing. This wall is applying a moment at A, and that moment is a counterclockwise moment, so I'm going to write plus MA. Now, here's where students get confused. They think this MA and this MA is the same thing, and they're not. This is the sum of the moments about point A, but there is a moment applied by the wall at A as well. These are different things. This is just one thing that contributes to this sum. The forces also cause a moment about A. So I won't show you all of the algebra. You know what force F is equal to. We found that earlier. That's 1,500 pounds. Let's see, units are all consistent. Foot-pounds, foot-pounds, let's see, yeah, foot-pounds there. And so MA will come out in foot-pounds. And in fact, the moment at A comes out to 6,750 foot-pounds. So now we've got all of our reactions. That was the whole point in drawing these free body diagrams. We haven't yet answered the question, which is what are the shear and moment within the beam? But I just want to make some notes. Maybe we'll go with a different color. Well, that one doesn't even write. Let's try another color. There we go. The reaction at A was 3,000 pounds. That's the force reaction. The moment reaction at A was 6,750 foot-pounds. The reaction at C was 1,500 pounds. And finally, we calculated an internal force at the pin. I'm just going to pull a line off there and say 1,500 pounds of force. Notice something interesting about this problem. This pin means that the beam can have no moment at that point because it can simply pivot. So we know the moment has to go to 0 at point B. But let's start off by taking a free body diagram of a beam segment where we have cut the beam well before we get to B. Okay? Now, obviously we have RA acting on it, MA acting on it. We've got some shear V we'd like to know the magnitude of at some moment within the beam besides this external moment reaction applied by the wall. We've got the distributed load of 500 pounds per foot along the top of the beam, and we've cut the beam at some particular position X. Well, what will we do? Well, the same thing we do all the time, apply the equations of equilibrium. We've got a new free body diagram here, a new toy to play with. Let's play with it. So let's sum forces in the y direction. We'd have what? RA acting up, minus V acting down, minus 500 pounds per foot times x feet. Okay, that sum should come out to 0. So since we know RA at 3,000 pounds, we can say that the shear V, solving for it, just pull it to the other side, is 3,000 pounds minus 500x. Of course, the x needs to be in feet, and then we'll get out shear in pounds force here. So if we cut the beam between A and B at any point x, this is the magnitude of the shear we will find. Let's sum moments about point A, taking counterclockwise as positive. Well, as we discussed, one of the external moments is the reaction moment at A that contributes to the sum of all the moments about point A. However, now we've got a moment within the beam as well, called M. If we're summing moments about point A, well, let's see. The shear V causes a moment at position X, right? Because the moment of the shear is Vx, and it's a negative moment with the way we've drawn this. But also the distributed load, which has a resultant, must cause a moment as well, and its moment will also be negative. Now the resultant of the 500 pound per foot load will act at the center of this segment. So let's calculate the magnitude of that resultant, 500 pounds per foot times x feet, same resultant we had before, but now we need the moment of that resultant, so we need to multiply that force by the moment arm, which is simply x over 2. And this is the sum that needs to come out to 0 for the beam to be in static equilibrium. Now our question is, what's the moment within the beam? That's what we're solving for. In other words, since this is the shear as a function of x, what's the moment as a function of x? We'll just solve for it. It'd be what? Vx, well, let's put it in order, minus ma plus Vx. Notice I'm just pulling everything to the other side. Plus, well, let's see, 250, because 500 divided by 2 is 250, times x squared. We've got two x's here to deal with. Okay. But we know that the moment is 6,750 foot-pounds, so that takes care of MA. Notice the negative sign came from the equation. Plus the shear, which we can plug in the equation for shear, 3,000 minus 500x times x. So in the parentheses, plugged in the equation for shear, and then don't forget the x, plus 250 x squared for the last term. I'm running out of space here. Let's see. If you simplify that, what would happen? Well, let's see. We'd get an x squared term here, an x term here. So we'd get negative 6,750 plus 3,000x. And then this minus 500x squared plus 250x squared would end up giving us just, what, negative 250x squared? So let me use the magic of the eraser board to combine those two terms. I think that's it. There. So negative 6,750 plus 3,000x minus 250x squared. And of course the units will be in foot-pounds. Whereas of course the units here are in pounds. And of course we need to plug x in the proper units of feet. All right, so we worked hard, but there are the equations that we need for the shear moment, at least in the segment from A to B. Now, what about the other segment? What about, if we consider an x-axis that begins here at A, what about when we go over to 3 foot, we take the other segment of the beam, segment 2, and we cut it so that we can expose the shear and the moment within the beam. We still have our distributed load, obviously, 500 pounds per foot. But now, of course, we have the force F pushing up. Now, why didn't we see force F when we went from A to B? Well, what we're doing is approaching B. If you plug into this equation x equal 3, what you'll find is that there's still a load of 1,500 pounds that needs to be accounted for. And that's what F does at the end of the beam. But over here, of course, we begin with the left-hand side. So we have to include that load in the beam from the very beginning. And we're going to cut the beam at some position x. Now be careful, x is measured from 0 there. So, first things first, some forces in the y direction. Well, there's F acting up, there's V acting down, there's 500 pounds per foot times how many feet? Well, it would be x minus 3. Okay? Remember, I'm measuring x from the very beginning, from the wall, from point A. But this needs to come out to 0. So, solving for the shear, which is what we want to know the shear within the beam. Solving for that shear, we'd have what? F minus 500x plus 1,500. So let's write that as 500x minus 3. And then, I guess we'll go space here. F is 1,500. And then minus 500x plus 1,500. And looks like these two will cancel. Or not cancel, excuse me, they'll combine. So 3,000 minus 500x. Is it a surprise that we have the exact same equation that we had before? Well, not really. The pin doesn't affect the moment, or doesn't affect the shear, it affects the moment. So we get the exact same equation that we had before. What about if we sum moments, say about point B, taking counterclockwise and positive? Remember, B is over here, whereas A is over here. You can sum moments about A if you want, it doesn't make any difference. You'll get the same thing. I just chose to sum moments about B. Well, let's see. We've got a resultant that would be causing a negative, or would provide a negative moment about B. And of course, the amount of it that we have is 500 pounds per foot times x minus 3 feet. Clear that those two cancel. But that's just the resultant of this distribution, depending on how far we cut the beam, right? Depending on where we cut the beam between B and C. I want the moment of that resultant, or yes, resultant. Sometimes I confuse reaction and resultant. I want the moment of that resultant. Well, what I need is the distance from here to halfway over, right? So how do I calculate that? Well, all you have to do is take x minus 3 over 2. Because remember, the distance between these two is simply x minus 3. I want half that distance, no problem, just divide it by 2. And then the shear will also cause a moment. The moment arm of the shear is simply x, so I will write, well, not exactly, it's x minus 3, right? Because I'm summing moments about B. So the moment arm of the shear is x minus 3, so I'll write minus v x less 3. What else? Well, there's the moment within the beam that is a positive moment, so add that in, and that's it. This should all sum to 0. Understand? Just as before, what I was looking for was shear, now I'm looking for the moment within the beam. So, solving for that moment within the beam, what will I get? Well, let's see, this is going to be a little bit of a mess. Let's go ahead and multiply these through, so, and pull them to the other side, because understand this moment's positive, so I'm going to pull this term to the other side. That changes the sign, so 500x changes the sign, don't forget. 5 times negative 3 would be minus 1500. But this whole thing needs to be multiplied by x minus 3 over 2. And then we know that the shear, remember I'm pulling it to the other side, so make that negative positive. The shear is 3000 minus 500x. That is the shear, and it needs to be multiplied by x minus 3. Okay. I guess I could have combined these two terms and then performed the multiplication. It would have been a little easier, but oh well, I didn't. I won't show you all of the algebra in between. I'll just show you the final result. I got negative 250x squared plus 3000x minus 6750. Does that sound familiar? It should. Exactly what we got before. Negative 6750 plus 3000x minus 250x squared. So the shear and the moment equation are the same throughout the entire length of the beam. So, now let's make shear and moment diagram. So I don't really need both of these, they're duplicates. Basically, this equation for shear and this equation for moment will work along the entire length of the beam. So the shear in pounds along the length of the beam in feet. Well, what does it look like? Well, if we plug in x equals 0, we get 3000. At x equals 0, we get 3,000 pounds. And of course, the slope, since this is just a y equals, well, b plus mx form, is negative 500. So we lose 500 pounds every foot we go along. Well, how long until we lose all of it, right? How long until the shear goes to 0? Well, let's see, what would it be? 6 times 500 would be 3,000. So apparently, at 6 feet, understand it's x equals 6 feet, the shear goes to 0, and it's just a linear decrease in shear from there to there. Once you get out to the end of the beam, what do we have? Well, that's an x equal to 3 plus 6 is 9. 9 500s are 4,500, so that'd be negative 1,500, right? So we end up at negative 1,500 pounds. Well, fortunately, we've got a reaction there that pulls us back up to 0 because we're out of beam once we get to C. Okay. What about the moment diagram in foot pounds? All we've got to do is plot this equation. Well, let's see. At x equal to 0, we get negative 6,750. Negative 6,750 foot-pounds. What about at x equal to 3? Remember, we said the moment should be 0 there. At x equal to 3, let's see, we have what? 9,000. 9 times 250. I'll let you do the math. It turns out it works. At x equal to 3 foot, the moment goes to 0. Now understand, this is the equation of a parabola. It's second order in x. And since the shear goes to 0 at this point, it turns out that is a maximum. So if you plug in x equals 6 in this equation, you will calculate the magnitude of the moment. It looks like I neglected to do that. I have to grab a calculator and do that. But let me go ahead and draw the shape. And if you plug in x equal to 9, you'll come back to 0 at the end. And so you just need a parabola connecting these points. Now my sketch is not the best, but you get the idea, I hope. I meant to calculate the magnitude of the moment at this point, and it looks like I neglected to do so. So let's grab a calculator and do that quickly. All right, so at x equals 6, all I got to do is plug 6 into this equation. 3 6s are 18, so 18,000 less 6,750 minus 250 times 6 times 6 is 36. So I got a maximum moment of 2250 foot-pounds. So that should give us the shear and moment diagrams for the beam with all of the relevant information along the length of the beam.